So frequently in physics lab, you are asked to work with the uncertainty in your input variables and output variables. By input, what I mean is variables that you have some measure of control over. You're turning a knob to set them, or you're selecting the resistor that goes in the circuit. It's some value that you have control over. Then output is the thing that happens as a result. It's the dependent variable that depends on all of the inputs that you're working with. The reason we need to think about this uncertainty stuff is because each of these things that you're working with as an input, you have a value for. So like you might have a value for B, and you might have a value for C. So let's call this one B and this one C. And you're looking to multiply those two values together. They might also be raised to a power, M or N. We'll just work with simple multiplication right now because I don't know how to draw this in m by n dimensional space. So the reason we need to think about this uncertainty stuff is because if I just take these two numbers and multiply them, right, to think of multiplication as kind of giving you an area because you're taking something by something multiplied by something. And so in principle, that would give you this shaded region of B times C, right? Except that B and C always have a little bit of uncertainty associated with them, right? So they've each got a little bit of a sigma associated with them. This might be a sigma B. This one we would call sigma C. And the sigma just means the fuzziness in the number, meaning I'm pretty sure B is equal to 5, but it could be as high as 5.1 and it could be as low as 4.9. So we're going to call it B equals 5 plus or minus 0.1. It's that wiggle room, that fudge factor, that margin of error that we usually just talk about qualitatively, but the sigmas give us a way to quantify that concept. Because if I think about it, what the sigmas are doing is saying, here is the average value, here's kind of the expected value of B, but it could be as high as this, it could be as low as this. And you can see that's really going to affect the area of my rectangle, because if it's as low as this, I'm only getting this much area, but if it's as high as this, I'm actually getting this whole larger rectangle. Same thing with C. I get a little strip of area over here, and so by the time you multiply those together, my actual answer, the thing that it is in reality, could be as small as this little rectangle, or it could be as big as this larger rectangle. And so what the difference in those rectangles represents, if you go from the small rectangle to the big rectangle, that represents sigma A, the uncertainty in the output. And you can see, because you're multiplying these, it can do all kinds of stuff, right? I can go from a relatively small uncertainty in B and a relatively small uncertainty in C. I can actually end up with a pretty high uncertainty in A, which is why it's critical that we take many, many data points so that we minimize this amount of uncertainty. So here's how this works out in practice. During the experiment, I find out what sigma B and sigma C are. Maybe I look it up in the manual I'm working with. Maybe I do some kind of test on my data to get an idea of what those uncertainties are. But the important thing is I know what the uncertainty in my inputs are, and I want to find out the uncertainty in my output, right? I want to know what is the range of values here between the small rectangle and the big rectangle in my final result. The way I calculate that is by getting the fractional uncertainty in A. Fractional uncertainty just means it's my uncertainty expressed as a percentage of A. In other words, if this is 5 and this is 100, then I'm off by 5%. The way I like to think about fractional uncertainty is with two extreme examples. Let's suppose I am doing an experiment that involves measuring length, and I discover that my uncertainty, my sigma length, is 1 inch. Is an inch a significant error in my length measurement? Well, it depends on what I'm measuring. If I'm trying to go to the moon and I'm trying to land in a specific crater in the moon, and I aim for the center of that crater and I'm off from the center by 1 inch, then that's a huge victory, right? An inch is nothing compared to either the size of the crater or the distance from the Earth to the moon. I have pretty much landed in the center. Nobody can tell the difference an inch makes when you're landing on the moon. It's very small fractional uncertainty. On the other hand, if I'm playing football and I am trying to score a touchdown, an inch is the difference between, yes, you scored a touchdown and now it's time to punt, right? So it depends on the problem you're working on. That's why we have to use this fractional uncertainty, because the error in and of itself doesn't give us enough information. The fractional error is what gives us an idea of whether the error is significant or not. The way you calculate this based on sigma B and sigma C is a little recipe. You start with a square root, so everything we're doing after this is underneath the square root sign. You take the power that was up here and you multiply it out in front under an absolute value. It's a bit like the power rule if you've had Calculus 1 for some very calculus-y reasons that you can get into on your own if you want. But what you do is you take this power, the thing that's in the exponent, multiply it out front. Then you take sigma b, divide it by b, so you're taking the fractional error in b and you're squaring it. Then you do the same thing for c. You add a plus sign. You do the same thing for c. You drop the exponent, so the thing that was up here, you drop down in front, and you take sigma c over c quantity squared. It looks a little bit like the Pythagorean theorem because it's the square root of one thing squared plus another thing squared. Again, for some very intricate mathematical reasons that you can read about if you're really interested. And the neat thing about this is you can do this as many times as you need to. So if you have a third thing on here, if you've got d to the k power, you would just add on the inside here absolute value of k, sigma d over d squared. If you've got a fifth thing, you just keep adding them on. A fifth thing, a fourth thing, however many. Let's go back and say if you got a fourth thing. And the beauty of this is you can just keep going with however many inputs you have. If you've got a fourth input, that's a pretty complicated experiment, but if you've got a fourth input, you would just add it in here, a fifth, a sixth, however many you have, you just keep adding. It's just the same procedure. You just place them all underneath the same square root symbol so that they're all getting added and then square rooted. Let's try this out in an example. Let's suppose I'm working with a circuit and I measure the current to be 2 amps with an uncertainty in my current of, let's say, 0.1 amps. So immediately what I can do with that is I can think about sigma current over current, right? Because I can think of this this 0.1 amps. Is that a large error? Is that a small error? I don't know because I have really no intuitive sense of how big an amp of current is. It's not something I measure every day. So I take that and I divide it by 2 amps, the value that I measured. I take 0.1 over 2 amps. Those amps will cancel, and so I'll have a 0.05. That's my fractional uncertainty, which is the same thing as 5%, because you know by now to go from a decimal to a percentage, you just move the decimal place twice. So it's a 5% uncertainty in the current. It's not great. It's probably going to cause me trouble down the road, but it's at least not 100%, right? It's at least under 10. Then we can do the same thing with the resistance in the circuit. So my resistance, let's say, was 100 ohms. These are just values I'm getting from an experiment. It doesn't matter how, because I use the same uncertainty formula no matter how I got these values. With a sigma r, let's make that smaller fractionally, 0.5 ohms. And so now I can figure out that my sigma r over r is going to be a 0.5 ohms divided by the value, 100 ohms. That one is a 0.005 or 0.5%. So I've got one fractional error of 5%, one fractional error of 0.5%. It is a good habit to go ahead and evaluate the percent uncertainty every time you get a sigma and a value, because it gives you an idea ahead of time of how good the data was, right? My resistance data, pretty good, only off by 0.5%. My current data off by 5%, that's going to be the thing that causes me trouble in a little bit. Let's suppose in this experiment I was interested in the power produced by the circuit. This is not something we've talked about in my Physics 2 lab yet, but if you want the power, the rate of energy transfer in the circuit, that's equal to the current squared times the resistance value. So if I just use my measured values, if I just use these two, I've got a 2 amp squared times 100 ohms. 2 squared gives me 4. 100 gives me 2 zeros over here. An amp squared times an ohm. We're not going to work out the units here because I hate working with the units for ohms, but that comes out to be watts because it's a power measurement. So that's the size of this middle rectangle here. That's the expected value for the power. But it could be smaller or it could be bigger because this current value, this could be as low as 1.9, and this resistance value could be as low as 99.5, which would give me a lower value for this. This current could be as big as 2.1, and the resistance could be as big as 100.5. You can think of that as being like, here's the smaller rectangle, here's the larger rectangle. How do I find out what the error is, what the error is here for the rectangle, for the power? Well, I use this equation over here. So I say that the sigma for the power, the uncertainty for the power, divided by absolute value for the power is going to be square root. We got to take each piece of this equation. First, let's take the current piece. So I take the 2, drop it down here in an absolute value, and then I take sigma I over I squared, plus do the same thing for r. This thing has a 1 up top, so I multiply by a 1 in absolute value. Not really necessary to write that, but for completeness sake, we'll put it there. And then we take sigma r over r, square it, and that's it, right? I don't have anything else involved here. I just have these 2 measurements. So this is going to give me the fractional error in the power. So this is going to be a square root of 2 times sigma I over I. Well, I've already calculated that as 0.05. So I can take my 0.05 and square it. Then I can take my fractional error in the resistance, which I've already calculated. That is my 0.005. Yes. 0.005 and square it. Right, so this is all numbers that I have from the experiment. It's just a question of how I combine them. This is also why it's useful to go ahead and calculate those fractional uncertainties when you first get access to them, because then you can just plug them in here. You're not worried about juggling 6 different numbers in here. You're only juggling 4. I assume 4 numbers is easier than 6. Maybe it is, maybe it's not. So you put this into a calculator. As always, Google is the best calculator around for number crunching. So 0.07 is what you get out for this, which corresponds to about 7%. So you notice it's a little bit higher than the error in the current, because we got error in the current and error in the resistor, but it's mostly around the same size as the error in the current because the error in the resistor is not contributing too terribly much. You also notice that it's getting exacerbated by this factor of 2 here, because whatever error I have in the current is going to show up twice because of this squared factor that we have here. And so if I want sigma p, right, this is sigma power over power, right, I can just take my 0.07, multiply it by the absolute value of the power here. Sigma power is going to be 0.07 times 400, which Google kindly tells me is 28 watts. So my final answer that I put in my lab report is that my power is 400 watts plus or minus 28 watts. And again, this is where the fractional error is crucial, because I have 28 watts as my error. I don't know whether that's a big error or a small error, so I have to compare it to the 400. Comparing those two gives me 7%. It's not great, but it's at least under 10. So there's a review and an example of how we work with this uncertainty map. It is the same process each time, just different powers involved and a different number of factors involved, but you just repeat that process every time. Keep track of your fractional uncertainties, and you can get the uncertainty in the final result in just a few steps.